Welcome to Educate. We are going to study the numericals on chapter 5 of class 12 physics. So let's start. Question number 1. A short bar magnet placed with its axis at 30 degree with a uniform external magnetic field of 0.25 Tesla experiences a torque of magnitude equal to 4.5 into 10 power minus 2 joule. What is the magnitude of magnetic moment of the magnet? So here our concern is to find magnetic moment, and you know tau equal to mb sine theta. So we can find m equal to tau divided by b sine theta. In our question, value of tau is given with uniform magnetic field is this much, and value of torque is 4.5 into 10 power minus 2. So 4.5 into 10 to the power minus 2 divided by B, strength of magnetic field is 0.25 into sine theta, sine 30 degree. Sine 30 is equal to how much? 1 by 2. So 1 here, 2 here. So further, we can write it 9 and then 9.0. So 9.0 into 10 to the power minus 2 divided by 0.25. So equal number of decimal places if we write. So this will become 900 divided by 25 into 10 to the power minus 2. So this 4 times. So this will become 36. So 36 into 10 power minus 2. And then we can write the unit joule per Tesla. Did you understand? The values are, this is value of magnetic field, this is value of torque, theta is given as 30 degree, and we can evaluate. So any doubt? I think no. Next is question 2 says a short bar magnet of magnetic moment m equal to 0.32 joule per Tesla is placed in a uniform magnetic field of 0.15 Tesla. If the bar is free to rotate in the plane of the field, which orientation would correspond to its stable, unstable equilibrium? What is the potential energy in each case? I told you earlier also, if theta is 0 degree, in that case we say that equilibrium is stable. If theta is 180 degree, then equilibrium will be unstable, right? So if you remember, u equal to minus mb cos theta. So here we have to find out the value of potential in case of stable and unstable. So in case of stable, theta must be 0 degree. So we have to put the values of m. So m is given as 0.32 and the magnetic field is given as 0.15, and then we can evaluate this much joule. This is case of stable. When it is unstable, so u will be equal to minus mb cos, this time 180 degree. Here we have taken theta equal to 0 degree and cos 0 degree is 1. Here if we write cos 180 degree, so cos 180 is minus 1, so this will become plus mb. So value will remain same thing. We will get 0.32 into 0.15 and joule. You can multiply to get the result. Question number 3. Question number 3 says a closely wound solenoid of 800 turns and area cross section 2.5 into 10 power minus 4 meter square carries a current of 3 ampere. Explain in which sense does the solenoid act like a bar magnet? What is its associated magnetic moment? So this is same thing. If you consider a solenoid, then you have to check the sense of current, like this. Suppose this is battery, this is key, and current is flowing like this. So here from inside, if you observe, so here inside, what will be the situation? If it is like this, current is going like this, so from inside, if you observe, it will be south pole. Here it will be like north pole. So if you write here N, not here, so you will see that this is north pole. Correct. From outside, if you observe, then what will happen? It will look like north pole, and this will look like south pole. Here, if you consider inside, so like this. So it is the current, the sense of current will decide what type pole will be there. So our concern is to find out magnetic moment, and magnetic moment can be found by formula M equal to number of turns into current into area of cross section. Number of turns is given as 800, and the current through it is given 3 ampere into area of cross section is 2.5 into 10 to the power minus 4, and the unit will be joule per Tesla. So you can easily evaluate. Let's go to next question. Question number 4 says, if the solenoid in question above is free to turn about the vertical direction and a uniform horizontal magnetic field of 0.25 Tesla is applied. So above case we are considering, it means we have to take the same M as we have got in first case. So in first case, if we evaluate, we would get M equal to 0.6 joule per Tesla. Here, if the solenoid in question above is free to turn about the vertical direction and uniform magnetic field exists, so value of B is given as 0.25 Tesla, right? What is the magnitude of torque on the solenoid when its axis makes an angle of 30 degree with the direction of applied field? So very simple, torque can be found by mv sine theta, right? So we can put the values 0.6 into 0.25 into sine is given as 30 degrees, sine 30 is 1 by 2. We can evaluate it. This will become how much? 7.5 into 10 to the power minus 2 joule. Correct? Unit of Tesla, sorry, unit of torque is either joule or Newton meter. Now, there is another question. Question says, a bar magnet of magnetic moment 1.5 joule per Tesla lies aligned with the direction of uniform magnetic field of 0.22 Tesla. It's simple. Now, what is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment normal to the field, means it is to be rotated through 90 degree, opposite to the field direction through 180 degree, right? So first case, we can write the formula for work done, that is case of potential energy. So it will be minus mv, and then we put the values. One will be here, theta is given, so we are starting from 0 degree to 90 degree, so we can write cos 0 degree minus cos 90 degree, and we can evaluate, right? So how much would it be? So cos 0 degree in first case, but it was in our question, it was aligned with the direction of magnetic field. What is the amount of work required to exert torque on the, so it's magnetic moment normal to the field. So we have to write, we can evaluate it, so it will be how much? So we evaluate the two cases and then we find the difference, right? So it will be mb sine 90 degree, and we are calculating it, so it's okay, correct? Now we are going to do, so this is first case, and then second case we can see what is that. Is there any confusion? Because I think once again let's analyze it. So here, a bar magnet of magnetic moment 1.5 joule per Tesla lies aligned with the direction of the uniform magnetic field of this much, right? They both are along same line. Now here what is to be done? This is to be rotated through 90 degree. So we find what is situation here, what is situation here, and then we find the difference. So what is formula? Formula is work done equal to potential energy minus mb and then cos theta, right? So here theta equal to initially, theta equal to 0 degree, this is initial. So you can say work done in this case, suppose we write it W1 initial. So it will be minus MB. And now we take theta equal to 90 degree. In that case, we find W2, right? So that will be 90 means 0. Then we find W2 minus W1. That will be plus MB, right? And then we can put the values. M is 1.5 and B magnetic field is 0.22 joule. We can evaluate, right? Then second part, let's see. Second part is opposite to the field direction. So here again, what you have to do? So W1 you can say minus MB cos 0 degree, right? So it will be minus MB, and then you have rotated it through 180 degree. So W2 will be equal to minus MB into cos 180 degree, and cos 180 degree is minus 1. So this will become plus MB, right? So if you find the difference W2 minus W1, so it will be 2 MB, and then you can put the values twice of M. So M is equal to 1.5 and then B is 2.2, and then evaluate. So it will be double of the previous case, correct? And then comes question number 6. A closely wound solenoid of 2000 turns and area of cross section 1.6 into 10 power minus 4 meters square, carrying a current of 4 ampere, is suspended through its center, allowing it to turn into a horizontal plane. What is the magnetic moment associated with the solenoid? So first of all, we are going to evaluate magnetic moment. So for that, if you remember, M equal to NIA. So what all we need? We need number of turns. Number of turns are 2000. Then current is given as 4 ampere into area is given 1.6 into 10 power minus 4. Now we can evaluate it. So that will come out to be 1.28 ampere meter square, right? And then comes what else they're asking. In second part, they are asking what is the force and torque on the solenoid if uniform magnetic field is set up at 30 degree with the axis of this. So that force is 0, as you know, but torque will be there because field is uniform, so force will not be there. And torque can be found by putting formula tau equal to mb sin theta, right? So mb, so m we have already found, that is 1.28, and magnetic field is given as how much? This much, 7.5 into 10 power minus 2. 7.5 into 10 power minus 2 into sin theta, sin 30 degree is 1 by 2. So we can evaluate, and this comes out to be 0.048 Newton meter. Up to here, no problem. Now, this is the last question. Let's see what it is. A short bar magnet has a magnetic moment of this much. Value of M is given. So M is given how much? M is given 0.48 joule per Tesla. That is okay. Then give the direction and magnitude of the magnetic field produced by the magnet at distance 10 cm from the center of the pole on the axial point. So you know if this is north, this is south, and then we evaluate it on its axis, we can find here, and then we take on this also. So suppose axial point is taken, then along SN, and in case of equatorial point, this will be along NS. So let's evaluate it. Direction you can easily decide if you have studied the derivation, how to find that. Suppose you are given a magnet and you have, suppose this is a magnet and this is north pole, this is south pole, or just make opposite, say this is south pole, this is North Pole, and if you find magnetic field at this point, so what will be the direction? It will be like this, because this is closer. So from south to north, if you take here, then it will be towards south. So that thing they are saying. So you can analyze that thing. That is simple. Our concern is to evaluate the magnetic field. So on axial point, if you remember, the magnetic field is given by B equal to mu naught upon 4 pi times 2m divided by r cube, right? So here we have values. Mu naught upon 4 pi becomes 10 power minus 7 into twice of magnetic moment. Magnetic moment is given as 0.48 divided by r cube. What is distance? Distance is 10 centimeter. So 0.1 whole cube, and this is Tesla. You can evaluate. Now just on evaluation you will get as 0.96 into 10 to the power minus 4 Tesla, right? And then comes another second part. This is for axial point. Now we take equatorial point. So be equatorial, it will be half of this value, whatever value it is, and its direction will be just opposite. So you can directly write 0.48 into 10 to the power minus 4 Tesla, right? You can also write, if you remember, 1 Gauss equal to 10 power minus 4 Tesla. So in terms of Gauss, if you write, so these negative powers will be removed and your answer will be 0.96 Gauss and 0.48 Gauss. So this is how chapter 5 is over. In next lecture, we will study next chapter. Thank you for watching. Team Educate.